Here are some work and energy and power practice problems. So first question, a box is pushed to the right with a varying horizontal force. That force is shown here. Just to make it clear, I'm going to highlight it here. Use a different color. So if you can't see, there's actually a data here. So there's a constant force at 6 newtons for a distance of 3 meters, and then it drops down to 0 at 6 meters. So the accompanying graph represents the relationship between the applied force and the distance the box moves. What is the total work done in moving the box 6 meters? So what we can do here is calculate the work done during the first 3 seconds by using the equation work equals force times displacement. That's from 0 to 3 meters. And then we can find the work done from 3 to 6 meters and use the average force in this during this displacement. Force times displacement. And we would add these two values together. So during the first 3 meters, it's 6 newtons times 3 meters. And that would be 18 joules. And during the next 3 meters, the average force here is just 3 newtons because the initial force is 6 and the final force is 0. So we use the average force of 3 newtons times 3 meters, and we would get 9 joules. And so the net work done is going to be equal to the sum of those two, and we would get 27 joules. Another way to solve this problem is to just look at the area under the graph. So if I'm able to find the area here, that's going to be equal to the work done. So the area here is 6 times 3, so that's 18 joules. And the area of this triangle is going to be 1/2 base times height. So it's half of 18, so that's going to be 9 joules. And then we get a total of 27 joules. So the answer is 3. So this 18 corresponds to this area here, and this 9 corresponds to this area here. Okay, next question. And so of course I recommend trying these problems. So maybe pause the video, give this a try, and then you can watch the solution as I go through it. So here we have a 250 kilogram car that is initially at rest at point A on a roller coaster track. The car carries the 75 kilogram passenger, and it's 20 meters above the ground. So all that information is shown in this picture here. So the first question is to calculate the total gravitational potential energy relative to the ground of the car and the passenger. So we have to use the equation. Potential energy is equal to mgh. So that's our equation. So we included our equation. Now we can show our substitution. And the substitution is going to look like, let me use a different color. Substitution is going to be gravitational potential energy is equal to the total mass is going to be 250 plus 75. So that's going to be 325 kilograms multiplied by, we'll use 10 for gravity. And the height is 20 meters. And that gives us an answer of potential energy. It's equal to, I'm going to use my calculator. And it's 325 times 10 times 20. And we get 65,000 joules of gravitational potential energy. The next question is to determine the speed of the car and passenger at point B. And point B is the lowest point on the track, which means all the potential energy that we started with is going to turn into kinetic energy down here. So to show that, we should show that this is a conservation of energy problem, where the initial energy and the final energy are equal. The initial energy is only gravitational potential, and the final energy is only kinetic. So this is our initial energy, this is our final energy. We know from the previous question that our initial potential energy is this. So I can really just write the equation. The equation can just be the gravitational potential energy is equal to 1/2 mv squared, where v is my unknown. And then my substitution with units would be 65,000 joules from my previous problem, equal to 1/2. The total mass is 325 kilograms, and I'm solving for v. So, I'm blocking this. But you can see that's all I would need to show for my equation and substitution. And then I'm going to do my calculation on my calculator. And the answer is going to be 2 times 65,000. And then I'm going to divide by 325. And take the square root of this value. So our answer is going to be 20 meters per second. So my answer V is equal to 20 meters per second. Remember that the equation and substitution is worth 1 point, and the answer with correct units is also worth 1 point. And here I have equation and substitution for 1 point, answer with units for 1 point. Okay. Next question, number 3. A 1/2 kilogram ball is thrown vertically upwards with an initial kinetic energy of 25 joules. Approximately how high will the ball rise? So this is kind of like the opposite of the previous problem, where it's still conservation of energy, but this time, this is final. This time we start off with kinetic energy, and we end up with gravitational potential energy. We know that the initial kinetic energy is 25 joules, so this value here is going to be 25. And the gravitational potential energy is mgh, where m times g is going to be the weight of this object, which is going to be 5 newtons, times h. And so we're solving for h. Actually, maybe I should show the steps here. The full equation is kinetic energy is equal to mgh. So everything that's known is this, and this. This is the only unknown, is h. And when I substitute in my values, I get 25 joules. That's given to us as the initial kinetic energy of 25 joules. And then the mass is given to us as 0.5 kilograms. We know that G is 10 for gravity, although you can use 9.8. And then we get 5 newtons here times h, which means the height is going to be equal to 25 joules divided by 5 newtons. And that gives us 5 meters as the answer. Here they have the answer as 5.1 because instead of using 10 for gravity, you use 9.8. It's close enough, but I know that this is going to be the correct answer. All right, number 4. A 2 kilogram block sliding down a ramp from a height of 3 meters above the ground reaches the ground with a kinetic energy of 50 joules. The total work done by friction on the block as it slides down the ramp is approximately. So here they're telling us that friction did some work. So let's just draw a quick sketch of what's going on here. It slides down a ramp. Let's say that's our ramp. And our block starts up here. At a height of 3 meters. From a height of 3 meters above the ground, yep. And so, of course, it has potential energy that it starts off with here. And it reaches the ground and it has a kinetic energy here of 50 joules. So that's given to us. This here, of course, is mgh. Now, normally these two values are going to be equal to each other. The initial potential and the final kinetic are equal to each other. But in this case, they're saying there's friction. So there's some amount of energy lost along the track here, along the ramp, that we're going to use Q to represent. So there's some amount of work done by friction that's going to be equal to the heat generated. And so this is our unknown. So our equation becomes energy initial equals energy final. The kinds of energies we have are gravitational potential, which turn into kinetic energy final, and heat, The initial potential energy is mgh, so it's a 2 kilogram block. So it weighs 20 newtons. 20 newtons times 3 meters. We should get 60 joules of initial potential energy. But when we get down to the bottom of the ramp, we only have 50 joules of kinetic energy. That means there is some heat generated, and that heat is equal to 10 joules. And that is the work done by friction. So work done by friction converts kinetic energy into thermal energy. That's what we have here. So the closest answer I see is here. Again, because in the Regents, they use 9.8 for gravity instead of 10. But again, the answer is close enough that I know which is the correct choice. So this answer here is 10. And this was 60 joules. So we can see the conservation of energy. We start off with 60 joules of energy. We end up with 60 joules of energy. Okay, number 5. During an emergency stop, a 1.5 times 10 to the 3 kilogram car lost a total of 3 times 10 to the 5th joules of kinetic energy. What was the speed of the car at the moment the brakes were applied? So I'm just going to draw a quick sketch just to help myself understand the question. Here we have a car that's going really fast. It has some initial kinetic energy. It then slams on the brakes and eventually comes to a stop here. So its final kinetic energy is 0 joules. So all the energy that it started off with here as kinetic energy was lost here as heat in the road and in the tires. The initial kinetic energy is 1/2 mv squared, and the thermal energy is just Q. There's no equation for Q, we just determined this value based on the context of the question. So we want to find out what was the speed of the car at the moment the brakes were applied. So we have to write our equation for conservation of energy. The initial energy is always equal to the final energy. The initial energy we start off with is just kinetic, and we end up with all the energy turning into thermal energy. This equation is 1/2 mv squared. This is just Q. Again, there's only one unknown variable here, and that's the V. So we can write out 1/2 times the mass of the car is 1.5 times 10 to the 3 kilograms times V squared, and the thermal energy, the car lost a total of 3 times 10 to the 5th joules of kinetic energy. And so we have to kind of interpret that as it turned into thermal energy. So that's 3 times 10 to the 5th joules of heat generated. So we can now solve for V. I'm going to use my calculator. And the answer is going to be 3 times 10 to the 5 times 2 divided by 1.5 times 10 to the 3rd for the mass. Then we take the square root of this value and we get 20. So the speed of the car initially was 20 meters per second, and so the answer is 3. Question number 6. Which graph best represents the relationship between the power required to raise an elevator and the speed at which the elevator rises? So whenever we have a graph question like this, where we're comparing two variables, I need to find the equation that has these two variables. And that equation would be power is equal to force times velocity. And then I isolate those two variables, power and average velocity, average speed, and notice that they are proportional to each other. And so the graph that shows the two variables being proportional like this is graph number 1. In other words, it's showing me a graph of y equals to x. Okay, question number 7. A 40 kilogram student runs up a staircase to a floor that is 5 meters higher than her starting point in 7 seconds. The student's power output. So this is a power question where we have a we can find out the weight of the student based on their mass. So we have a force. They run up to a position that's 5 meters higher. That's their displacement, and we're given the time as 7 seconds. So we get power equals the weight of the student is 400 newtons. The displacement is 5 meters, and the time is 7 seconds. And so the power, the student's power output is going to be 400 times 5 divided by 7. And the answer is 285 watts. And the closest answer we have is choice 2. Again, I use 10 for gravity. If we use 9.8, we'd probably get this value. Okay, number 8. A 70 kilogram cyclist develops 210 watts of power while pedaling at a constant velocity of 7 meters per second east. What average force is exerted eastward on the bicycle to maintain this constant speed? So we need an equation that has power and velocity. So that's going to be power is equal to force times velocity. The power output is 210 watts. The force is unknown. That's what we're trying to find out. What is the average force exerted? The speed is given to us as 7 meters per second. And so the force is going to be equal to 210 divided by 7. That's going to be 30 newtons. Okay, this is our last question. So I made this question to include more than just one type of energy. We have a 5 kilogram mass shown here, is held against a spring with a spring constant of 2,000 newtons per meter. The spring has been compressed 0.6 meters from its rest length, so the delta X value is 0.6. When released, how fast will the mass be moving when it reaches the top of the hill? So this block is going to be pushed by the spring. It's going to gain lots of kinetic energy here. It's going to then have to rise up this hill, losing some kinetic and gaining potential. And the question is, how fast will it be moving when it reaches here? What is the speed? So to solve this question, we have to use the conservation of energy again. Energy initial equals energy final. The types of energies that we start with are just elastic and, it's just elastic potential energy, and that's all. And then we end up with both gravitational potential and kinetic energies. Right, so once the block is up here, the spring is back to its rest length, and so there is no elastic potential energy in the end. So this is going to be 1/2 k delta x squared. This is going to be mgh final, and then this is going to be 1/2 mv final squared. The only unknown variable is going to be this v value. That's what we're looking for. So we can plug in the values as 1/2 times 2,000 newtons per meter. The compression is 0.6 meters squared. The weight of the block is 15 newtons times, it's going to be 3 meters above the ground, plus 1/2. It's a 5 kilogram block. And then we have Vf squared. So this is let's highlight our only unknown variable right here. That's what we're going to solve for. So I'm going to use my calculator to solve for the energy in the spring. That's 1/2 times 2,000 for the spring constant times 0.6 squared for the change in length. So I'm going to record that we have 360 joules of elastic potential energy. And then for the gravitational potential, it's going to just be 50 times 3. So that's 150 joules. Plus 2.5 kilograms times Vf squared. And so here I have to just solve for Vf. I'll use my calculator again. It's going to be 360 minus 150. And then we divide that by 2.5. And if we take the square root of this value, we'll get our answer. And the answer is about 9.2. V is equal to 9.2 meters per second.